This is what a lot of people think of when they think groundwater, an underwater river. And even though this is a really cool picture, this is not what groundwater, for the most part, is. Instead, it's a very small amount of water within a very small space. But that small amount of water actually adds up when you look at how much groundwater there is nationally and internationally. And it's extremely important. This is the largest available source of fresh water. So half of the drinking water in the United States, half of the irrigation water in the United States is coming from groundwater. From a scientific perspective, groundwater causes erosion in good ways and in bad ways, and it equalizes stream flow. And we'll talk a little bit about both those in just a minute. From a biological perspective, which we will not talk much about, it provides some very unique habitats. So the first thing to cover when you discuss groundwater is the difference between porosity and permeability. So most groundwater is not underground rivers flowing. I mentioned it's that small amount of water that's between particles. Porosity is the amount of empty space between particles. It's not the same as permeability. Permeability is a measure of how interconnected those pore spaces are. You can have a big pore space, but if water can't get into it, it's not going to be able to store water. So it's that difference between porosity and permeability that is the difference between an aquitard and an aquifer. An aquifer is an area underground that is very permeable. An aquitard is not permeable. So if all the ground was equally permeable, water would flow onto the surface and simply seep into the earth. Okay? There would be no shallow groundwater for us to pump out. Well, that's not the reality. As you go deeper into the earth, you'll encounter layers that have lower porosity and, more importantly, lower permeability. So at that point, water can no longer seep into the earth and it has to accumulate. Okay, now this scenario here also is not realistic because we know the Earth's surface is not perfectly flat. So instead, what we see is a scenario where water seeps into the earth, it accumulates on top of that aquitard, and it reaches the surface at streams, at swamps, at freshwater springs, and you'll notice that the groundwater surface is parallel to the land surface. Okay. So that groundwater surface is called the water table. Below the water table is the zone of saturation. That's where all the pore spaces that are permeable are filled with water. They're saturated with water. Above the water table is the zone of aeration, or the unsaturated zone. In this area, you still have some water, but not all the pore spaces are filled with water. So keep in mind that water has to pass through that zone of aeration, also known as the zone of, or the unsaturated zone, has to pass through that zone to get to the water table. So water is moving down through that layer toward the water table. It's also moving up via evaporation toward the surface to help form the soil moisture. So water is moving through that layer. It's not saturated in the pores, however. So when that water table encounters the Earth's surface, that's when we have streams, it's when we have springs. In the case of streams, we can have a gaining stream if the water table is sloped toward that stream surface. In that case, the groundwater is feeding the stream. If you look at the water table on the picture on the bottom, it's sloping away from that stream. In that case, the stream is a losing stream. Water is flowing from the stream into the ground. Now here's that other term that I mentioned, springs. It's another instance where the water table intersects the surface. And in many cases, it tends to be on more vertical surfaces than the boring case of a stream, like I showed you a minute ago. Hot springs are probably the most interesting kinds of springs. And there's a couple categories that we'll talk about. Most hot springs are going to form because of water being heated by igneous rock that is still cooling. And because that water is very hot, it's able to soak up lots of dissolved chemicals. And when it comes up to the surface, it quickly cools down. The water starts to evaporate, and all that chemical content is then precipitated out. Most commonly, it's going to form a rock called travertine, which is a type of calcite. Okay. Now, what you see on these ledges are layers of travertine. So it's calcite or limestone, if you want to call it that. In the middle part of this picture, you'll also see some yellows and some greens. Now, that's not mineral content. That's actually algae that's growing within the travertine. I mentioned the hot springs and geysers as well. Geysers are a special type of hot springs. Are mainly caused by mainly waters fed by the I mentioned that hot springs and geysers as well, geysers are a certain type of hot springs, are typically formed from waters that are being warmed by the cooling of igneous rock. And you can see in the western United States where there's been more recent volcanic activity, that's where we have most of our hot springs. But if you look in the eastern part of the United States, you see some dots in Arkansas, in Georgia, in Virginia, West Virginia, and one up there in Pennsylvania. Those are areas that are typically called warm springs instead of hot springs. The difference is not just the temperature of the water, but how the water is warmed up. In the case of warm springs, water infiltrates into the ground, often via a fault line, and it goes deep into the ground. As you move deeper into the earth, you have higher temperatures. So it's called geothermal warming. The water is warming up because of the depth within the earth. And then it's forced back up, and that new water is called a warm spring. In the case of hot springs, that water can be a couple hundred degrees. And that's especially true in the case of geysers. Geysers tend to explode because they're under great force. It's groundwater that is heating and expanding. It changes to steam and then it erupts. Now, the key difference between a geyser and other hot springs is how the plumbing works. In most hot springs, the big opening is not going to allow pressure to build up. In the case of geysers, there's an opening underground, a cavity where the water can accumulate, the cavity where the steam can accumulate, but there's only a very small opening at the surface. Now, instead of springs and hot springs and geysers, most of the way that we encounter groundwater is by pumping wells. And so we can drill a well and start pumping. Now, immediately what's going to happen is that the water table is going to dip toward that well. It's called a cone of depression. So this is a three-dimensional depressed area on the water table. This forms because even though water is trying to replace the water that we're pumping out, we can pump a lot faster than water can flow underground. Okay. So in areas where the water flows more slowly, the cone of depression will be even larger. Now, this is a problem because if you're a small water user and your well doesn't go deep enough, and your neighbor has a well that's pumping even more, that cone of depression can intersect your well and can actually pull that water table below where your well is. So what do you do at this point? Well, so far in the eastern United States, this has not been a major issue outside of Florida. It has been a major issue in the western part of the United States. And there are laws in many of the western states governing how deep you can drill your well and how fast you can pump, because that cone of depression doesn't just affect you, it affects the water table of your neighbors. So in the case of wells, we're typically pumping water up. But in some cases, water is going to rise up within a well naturally. So it may seem like water is defying gravity, such as in this case, a well is drilled and water rises up, although not all the way to the surface. So is it defying gravity? Well, obviously no, it's not. It follows a principle that you may have experimented with a little bit yourself. So if you put some apple juice into a funnel, when you raise one end of the funnel, the apple juice in the other end is going to rise up to the same level. So if you rise the funnel end all the way up and put the open end into your mouth, the water is going to flow via gravity into your mouth, even if your funnel is still pointing, even if your drinking end is still pointing up. Now the same thing happens underground. So water that flows up within a well on its own pressure is an artesian well. If it flows all the way up to the surface, it's a flowing well. If it just moves up a little bit, but not all the way to the surface, it's called a non-flowing well. Now this is obviously an old photograph, but it's one that I find very impressive. In central and southern Texas in the 1800s, desert area or very dry areas, but when people started drilling for water, they hit an aquifer. They created artesian wells, and these artesian wells had so much pressure that they were shooting water up 20 and 30 feet into the air. So this was fantastic. They could build cities around these artesian wells with this phenomenal amount of water. The problem is eventually that pressure is relieved. So after about 1 year of all these wells flowing around San Antonio, they were no longer spilling out onto the surface. There are still some places in central Texas and Florida and a few other places around the U.S. where you can have artesian wells, but they're obviously going to be short-lived. The reason artesian wells work is because they are responding to gravity. The key is that all the water within an aquifer, that blue shaded area in the big picture on the top, all the water in there is trying to get to the same surface, trying to get to that same level. So if you're closer to well 1 over here, that water is not going to make it all the way to the surface. But if you drill a well in area 2, that water is trying to come up to that pressure surface. So that's that one surface where all the water is going to balance out because of gravity. Now, groundwater does a little bit of erosion, and it deposits a little bit of sediment as well. In the case of erosion, it creates caves, it creates caverns. Caves and caverns are the same thing. In the case of depositing material, it creates speleothems within the caves. So caves are formed when the groundwater is high. So groundwater has to be high to dissolve the underground rock. And in most cases, it's going to dissolve rock that is limestone. In some cases, gypsum. It's rarely going to dissolve other types of rocks. Once the water table lowers and that cave is open to air, that's when deposition starts to happen. Water dripping into the cave can form speleothems. Speleo means cave, thems means things. So speleothem is anything in a cave. Stalactites and stalagmites are the two most general types of speleothems. Although if you go to a cave, you'll hear lots of terms like soda straws and french fries and cave bacon. Basically, categorize everything as a stalactite, something that's hanging tight from the ceiling, tight from the cave roof, and a stalagmite, which forms from the floor and might eventually reach up to the ceiling. Now, one issue with that erosive capability of groundwater is that when it forms caves, caves are not stable. So the next time you go visit a cave, realize that that ceiling is going to fall at some point. It's going to happen because it no longer has water in it to keep the roof up. Well, in the case of pumping excess amounts of groundwater, we do the same thing. We open up big cavities that are no longer supported by that water, and we can cause sinkholes, as you can see on the left. Or in more moderate cases, we can see subsidence. Subsidence being the gradual lowering of the land surface. So on the right, and in the course of about 50 years, you have the San Joaquin Valley of California lowered by about 30 feet. So this is a dramatic lowering of the land surface, and it's not just happening in the San Joaquin Valley. The same massive amount of lowering has happened in Houston and the Galveston area. Even more subsidence has happened in Mexico City. So we know that groundwater is a phenomenal resource for drinking water, for irrigation. However, we also know that it has potential problems if we pump out too much of it. There's another problem. Anything we dump on the surface can contaminate the groundwater. And I do see here that I misspelled the word contamination. So the contamination of groundwater is much more of a problem than the contamination of surface water. Because in the case of surface water, we can skim off the oil, we can block off part of it. In the case of groundwater, there's no way for us to go down there and to clean out every little pore space for an entire region. So in the case of groundwater contamination, it's essentially a permanent contamination. Once it's contaminated by sewage, by pesticides, by whatever, it's essentially contaminated for the lifetime of that aquifer.